Hello everyone and welcome. This video is all about sequence detectors. We'll be diving into the design of circuits specifically made to detect particular bit patterns within a stream of data. This is part of the Digital Logic and Design series, so let's get started. So, what exactly is a sequence detector? In simple terms, it is a digital circuit that looks for a specific sequence of bits in a continuous flow of input data. For instance, imagine you want to find the pattern 1011 in a stream of incoming bits. A sequence detector will output a signal when that exact pattern is found. Sequence detectors come in two main flavors: overlapping and non-overlapping. In overlapping sequence detection, sequences can share bits. For example, if you're looking for the sequence 101 and the input stream is 10101, the detector would recognize two instances of the sequence because they overlap. On the other hand, non-overlapping detectors require a complete reset after a sequence is detected. Using the same example, a non-overlapping detector would only find the first 101 and then reset, ignoring the overlapping 01 at the end. Now let's discuss how we design these sequence detectors. A common approach is to use a finite state machine, often abbreviated as FSM. The design using FSM involves three key steps. First, we define states that represent the progress of recognizing the pattern we are looking for. Second, we create a state transition diagram to visualize how the circuit moves between these states based on the input. Third, we implement this diagram using flip-flops, which are the basic memory elements in digital circuits. Let's solidify this with an example. Suppose we want to design a detector for the pattern 101. We'll need four states. State 0, which is the initial state. State 1, where we've detected a 1. State 2, where we've detected 10. And finally, state 3, where we've detected the complete sequence 101, and our output will be 1 to signal that the sequence has been found. To fully define our sequence detector, we create a state transition table. This table tells us what the next state will be based on the current state and the input. For example, if we are in state 0 and receive a 0 input, we remain in state 0. But if we receive a 1, we move to state 1. Similarly, the table maps out all possible transitions between states based on the input and indicates the output, which is 1, only when the target sequence is fully detected in state 3. Now let's see how we can express this in Verilog. Here is a snippet of the Verilog code for our sequence detector. We define a module named sequence_detector_101 with inputs for clock, reset, and data input, and an output named detected. We use a 2-bit register to represent the states and assign binary codes to each of the four states, S0, S1, S2, and S3. Inside the always block, which is triggered by the positive edge of the clock, we set the detected output to 1, only when the current state is S3, indicating that the sequence 101 has been detected. Sequence detectors have many real-world applications. They are used in protocol synchronization, frame detection, error pattern recognition, and security systems. In summary, finite state machine-based design enables efficient pattern detection in digital systems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.